You know, when most of us think about math, we remember these rigid rules we had to follow. But what if I told you that higher math is actually about creating new rules? Today, we're going to go on a little journey to see how mathematicians invent new lenses to see the world, and it all starts with something as simple as a line.
Remember those XY graphs from school? Over, up, plot the point. It feels so straightforward. But what if the rules weren't so simple? What if the very idea of a line had a hidden complexity? Like a secret checklist it has to pass just to even exist.
So our first stop is something that seems, well, totally obvious. An unbroken, connected line. It feels intuitive, right? But in math, intuition is just the starting point. It's where the questions begin, not where they end. To a mathematician, that simple, unbroken line has to prove itself.
Now, you've probably heard of the pen test. It's this really simple visual idea. If you can draw the whole graph without ever lifting your pen off the paper, it's continuous. It's a great starting point, but math can't really run on visuals alone. It needs cold, hard rules.
Yeah, see, to make that pen test totally airtight, mathematicians created a checklist. A function doesn't just get to call itself continuous because it looks the part. Oh no, it has to earn it. It has to pass 3 specific, non-negotiable tests at every single point. Okay, so here's that checklist. First, the limit has to exist. All that means is that the line has to be heading towards one specific value from both the left and the right. Second, the actual point has to be there, no empty holes in the graph. And third, and this is the big one, where the line is heading must be the exact same spot where it lands. If all 3 of those are true, congratulations, you've got an unbroken line.
So what happens when a function fails even one of those tests? Well, then we get what's called a discontinuity, basically a break in the line. And it turns out lines can break in a few really distinct ways.
First up, you've got a removable discontinuity. The best way to think of this is like a tiny single-point pothole on an otherwise perfect road. The road leads right to the spot, but the pavement is just missing right there. Then you have a jump. This is where the function is just cruising along at one level, and then bam, it's instantly at a totally different height. The line is literally broken in 2.
And finally, you get the most dramatic break of all, the infinite discontinuity. This happens at something called an asymptote. It's like an invisible vertical wall that the line gets closer and closer to, but it can never ever touch it. It just skyrockets towards infinity, creating this massive, uncrossable chasm in the graph.
Okay, so we've seen how math can add this incredible layer of precision to a simple idea like a line. Now let's take that a step further. What happens if we don't just change the rules of the line, but we change the entire map? What if we completely rethink our perspective on where a point even is? We're all used to the rectangular system, right? Go over 3, go up 4. It's like navigating a city grid. But polar coordinates ask a totally different set of questions. Instead of how far over and how far up, they ask, which direction should I face and how far do I go? You're basically shifting from a grid to a compass and a ruler.
And this isn't just some mathematical party trick. As Professor Leonard puts it, for certain problems, this new perspective is simply easier, nicer, or more relevant. It's all about choosing the right tool for the job.
So here's how it works. You stand at the center, which is called the pole. You turn a certain angle, theta, away from a starting line. Then you just walk forward a certain distance, r, and that's it. That's your point. It's just 2 simple instructions, angle and distance.
So why on earth would you invent a whole new system? Well, because the world isn't always built on a grid. I mean, think about the orbit of a planet, or the ripples spreading out in a pond. Trying to describe those with squares and rectangles is clumsy. Polar coordinates are the natural language of circles, spirals, and waves.
So we've seen how math can add precision and how it can offer new perspectives. For our final stop, we're going to explore one of its most powerful ideas, how to know with absolute certainty if something you've done can be undone.
I mean, think about it. You can untie a knot, but you can't unscramble an egg. Some processes are reversible, and some just aren't. In math, we use these things called matrices, which are just grids of numbers, to represent actions like rotating or stretching an object. And there's a way to know for sure if that action can be reversed. And here's the crucial insight. You have to get this. Not every action has an undo button. Just because you can do something doesn't automatically guarantee you can reverse it. Being able to go backwards is a special property. It's not a given. So how do we know? How do we know which actions are reversible? Well, the answer lies in this one single powerful number called the determinant. You do a specific calculation on your grid of numbers, and it all boils down to one value. And that one number holds the key to everything.
And the rule is surprisingly simple. If the determinant is anything other than 0, could be positive, could be negative, it doesn't matter. An inverse exists. You can undo the action. But if that determinant is exactly 0, the process is irreversible. There's no going back. It's a clear, definitive line in the sand. Okay, so we've looked at the strict rules of a line, a whole new way to map a point, and how to know if you can reverse an action. Now, they might seem totally disconnected, but they all showcase the same core idea of what mathematics is all about.
So what do we learn? We saw how math takes an intuitive idea, like a connected line, and gives it a precise, powerful definition. We learned that just by changing our perspective with something like polar coordinates, we can make really complex problems way simpler. And we found a tool, the determinant, that tells us if an action is permanent or reversible. See, the thread that connects all of this is that mathematics is so much more than just calculation. It's about building frameworks, creating new languages, and developing these incredible lenses that let us see the underlying structure of the world with a clarity you just can't get anywhere else. And that kind of leaves us with one final thought. Whether it's in your job, your hobbies, or just how you think about things, what part of your world could be understood in a completely new and maybe better way if only you had the right mathematical lens?